minute here. And then on Monday, we'll be going into Miller indices. It'll still be in the same set of slides that we have in the deck that's posted online right now. Okay, so last time we left with this problem, which was this idea of the radius ratio. And remember, radius ratio is a way of thinking about how ions fit together inside a lattice. And so we left, I think, with this problem where we said, look, you have two structures that actually exist in the real world for cadmium selenide. Depending on where they're made and the temperature they're made at and the pressure and so forth, it forms different both crystals. And so thermodynamically, they're both accessible. So we're asked, okay, which one of these two would we actually predict by the radius ratio rules? Either the one on the left, which is our rock salt structure, which has a coordination number of 6. So all of the atoms have 6 things in their nearest neighbors, and the Wurtzite structure on the right, which has a coordination number of 4. So the nearest neighbors for all the cadmiums is only 4 seleniums. Okay, and you're given the radii. So if cadmium is 4 coordinate, it tends to have a 92 picometer ionic radius, and if it's in 6 coordinate, that's a little bit larger, and it has a 109 picometer radius. And so then for selenium, pretty much it's the same in all its compounds. Again, those numbers are experimentally determined from kind of averages from lots of different structures that people have measured. And so this is the data that you're starting with and trying to figure out and predict which structure you would get. And then if you go through and calculate the radius ratios for these, you'd find that for 4 coordinate cadmium selenide, you get a ratio of 0.5, and for 6 coordinate, you get 0.59. And so if you look at where that fits in our table of where the radius rate, the table allows us to predict structures, 0.5 and 0.59 both are in between 0.4 and 0.7. And so that would give us a prediction of a 6 coordinate octahedral structure. And so, this Wurtzite structure, which is one of the 2 structures that cadmium selenide forms, actually violates the radius ratio rule. So the question is, why is that? And you might be able to figure that out just by looking at the structure in a way. This is a 4 coordinate structure, and so you can imagine these cadmium ions and the selenium ions are all basically sp3 hybridized. Back in the day when we were talking about organic chemistry, that terminology. So what does that mean? That means that there's molecular orbitals that are bonding these structures together. And so in the case of something like this, where you violate a radius ratio rule, you can no longer think of just simply packing the spheres together and what's the most convenient way to pack them. You actually have to think that actually bonds form. You have covalent bonding in addition to ionic bonding, and the covalent bonding gives you directionality. So covalent bonds have direction to them based on the orbital shapes. So ultimately, radius ratio helps you with really ionic compounds, but even in some cases where you would call something a very ionic compound, you still may find that covalent bonding kind of takes over and controls the structure a bit. Okay, so one last thing I want to just cover is a little bit on lattices. Now, I think it probably helps if you guys get some balls. So I brought these in here to kind of show you my demonstration. Little squash balls here. So here's 3 balls. I'm going to take a 4th one and pack it in like that, and that you can see makes a tetrahedron. You also will notice then if you look in the center of that, and I'm going to try to do this without my hand puppet. Let's see, you can't probably see that very easily. See the eraser here? Anyway, it's easier to see probably there. If you stick that into the middle of these 4 balls, obviously the gap, the hole that I'm sticking this eraser into, that is the, what we would call a tetrahedral hole. So where that eraser is sitting right now on this pencil is sitting in a gap or in a spot of vacancy. It's defined by these 4 balls, and that geometry, of course, is a tetrahedral geometry. So when the balls pack, we would consider that to be a tetrahedral hole. Now, to do an octahedral hole, it takes a little bit more marbles. So I brought this cool little device here with me, angled down my camera. All right, so I got some tubing here and I made a little circle, you can see, and then I'm gonna just pack these balls into the circle, and it perfectly makes a little hexagonal structure. Okay, so that would be a hexagonal close pack single layer structure. Let's go ahead and pack some balls on top of that. So we're gonna put the next layer of atoms on, and so I'm gonna do that. And you can see they kind of naturally fall into the little gaps. And that would be then the next layer of balls, okay? So you can do this at home, even if you don't have blue balls. And I know a lot of you probably do have blue balls because you're sitting at home in isolation, but you can also get blueberries. And so this is something that you all can access even if you don't have sporting instincts. So see, these are 4 blueberries. So you can take these 3 blueberries and out of the supermarket and then pack a 4th one on top like that and make your own tetrahedral hole. And so I recommend you guys, if you need to help visualize these things, go buy a pack of blueberries, get ones that are all about the right size, and you'll do it. Now, why did we do this? Well, I want to show you that there's also a thing called a tetrahedral hole. And so the octahedral hole. The tetrahedral hole is easy to see because, you know, basically anytime you put 4 balls together, you're going to have a hole in the middle. It's tetrahedral. But if you look at how this packs, and if I turn this way towards you guys, you can see there's three balls there. This one would, if this ball goes in there in the lattice, it would form a tetrahedral hole. But let's turn this a little bit, and you'll see there, there's 1, 2, 3, 4 balls. They actually form a square. And if the next ball comes in like that, what you'll notice is that actually forms what's called an octahedral hole. So there's 4 balls, 1, 2, 3, 4, this one on top. And if you look at this structure carefully enough with the right lighting, you'll see there's another ball down at the bottom of those 4. And so if you do that, you'll notice that you've made now in this structure, just by putting that extra ball into the lattice, there's a spot that we would call an octahedral hole. And so if you look in this structure and take a pencil and poke it into the different holes, you'll see that there are, when you pack balls together, both tetrahedral and octahedral holes in the lattice, okay? And why do I call them holes? Because they're little gaps that these balls have a certain radius to them, that, you know, there's gaps in between where those balls pack that other things could fit. And that's how we build up a lot of structures. So if you start going back now to our FCC lattice here, so this lattice that's shown on the chart is basically a representation of the structure that I just built with those balls, and except they aren't touching, they're going to shrunk them down a little bit so it's easier to see them. But this is also a face-centered cubic. This is has the same basic packing as the lattice that we just built. So let's take that and make a sodium chloride out of it. That's what we did last time. And there you would be placing these green, in this case, the chloride ions, into what were octahedral holes in that lattice. So again, we back up. That's our lattice. And if we look where are the octahedral holes, it may not be as obvious or easy to see it here as it will be in that physical model that I just built for you. But all of these little green guys, look at the one in the center here, is the most obvious and easy one to visualize. This little chloride here is sitting in an octahedral hole in the lattice. And you can see it there because there's 1, 2, 3, 4 nearest neighbors in that plane, one on top and one down below, okay? So that's how it works. And so that's an octahedral hole in that lattice, and that's how we would build the rock salt structure, by filling every one of those octahedral holes. When we pack the sodium ions together, we fill all those octahedral holes with chloride ions, and we make sodium chloride. Now let's go back to our original lattice, which just would show the, if it were rock salt, it would just be showing the anions or the cations. And then let's put something in the tetrahedral holes. Now, also, it's really hard to visualize there, but if you build your ball model, you'll see that there are spots in the lattice where the balls pack together, where there are little gaps that you can pack something that actually has a tetrahedral coordination. And I've shown that here. And what we've done there is we've taken the same FCC structure now, but we've replaced some of the atoms, or we've left the atoms on the lattice, some atoms on the lattice points, but we've added some additional atoms that are not on lattice points and put them into these tetrahedral holes. And so there's one sitting there, there's one sitting there, one there, and one there that we've added to that lattice. And that gives us our tetrahedral structure. And that's actually the diamond lattice. So you can see how those structures are built up. And that's actually all I wanted to do at this point. So I want to now, let's flip over into